Hello and welcome to all. In today's lecture, we are going to start the unit number 3, that is context-free grammar and languages. So in this unit, this one is the syllabus, and here in this unit we want to discuss introduction of CFG, regular grammar, context-free grammar, its definition, how to derive the derivation by using given grammar, language of grammar, sentential and past key of the given grammar, how to perform the derivation, how to draw the past key, ambiguity in the grammar and languages. After that, how to remove the ambiguous grammar, how to perform the simplification of the CFG by eliminating unit production, useless symbol and useless production, as well as epsilon production. Normal forms, in that we want to discuss CNF and GNF normal form, closure and decision properties of CFL, Chomsky hierarchy, application of CFG. So these points we want to cover or we want to discuss as a part of third unit. So first of all, we'll see what do we mean by grammar. So grammar is a set of rules which check the correctness of the sentence or the construct the sentence, correct sentence using these rules. So with the help of some set of rules as well as some syntax, we want to perform we want to generate the correct sentence. So syntax are nothing but the rules which are be used to form the sentence. Semantics represent the meaning of sentence. So sentence should be meaningful one, and language is nothing but set of valid sentences. Context-free grammar. So we know that with the help of FA, means finite automata, we can accept the regular language as well as we can describe the regular language by using regular expression. Means for example, if the language is L is equal to 10, 20, 30, 40 or 50 is there. Okay, like this, epsilon comma 10, 20, 30, 40, 50 like this. So what is the meaning of this language? This language indicates that it is a combination of any number of zeros. It is a combination of string of zeros including epsilon. Length is anything. So for this, it is possible to draw its equivalent finite automata. We can draw its equivalent finite automata. So we know that by accepting any number of zero, it will stay in same state, and initial state q0 itself to final state. So it's possible to draw its equivalent finite automata, as well as we can write down its regular expression. So regular expression is equal to 0 star, because star or clean closure indicate that any combination of the 0 or any combination of the given input alphabet. Here input alphabet is 0. But there are some languages which are other than regular languages. For example, if I will consider one more example, L is equal to 20, after that 30, after that 50, after that 70, 11, like this. Okay. So now it is not possible to represent this language. This language is nothing but prime number of this language is the prime number 0 is to p, where p is the prime number. Now here it is not possible to draw its equivalent finite automata, as well as not possible to represent this language by means of regular expression. So there is a need of another approach to represent such type of language, means non-regular type of language as well. So context-free grammar or grammar is another approach to represent the language. By using grammar, we can represent both language, regular as well as the non-regular language. It is possible to represent regular language with the help of grammar, and it is also possible to represent non-regular type of languages by using the CFG. In this approach, now in context-free grammar approach, language is represented by using set of equation, or language is represented by using set of production. In case of finite automata, we are having the transition. Here we are having set of equation of production. Equations are recursive in nature. Equations in the grammars are recursive in nature. Here you can see this a will appear on its right side. Okay, so these equations are a variable which will appear on right side. So these equations are recursive in nature. Finite automata which having set of state. In case of finite automata, we are having set of state. For example, here if I draw q0, after accepting small a, it will be in q1. So here in this transition diagram, in this finite automata, two states are there, q0 and q1. But in case of CFG, we are having variable. Instead of Q0, Q1, here we are having variable A. So in CFGs, we are having the set of variable. FA, find automata defined over an alphabet. So small a is alphabet. In case of grammar, it is called as terminal. For example, here A tends to small a, capital A, so small a is the terminals. So grammar defined over set of terminals. And FA having set of transition and grammar having set of equation. Transition means what? Here I can say Q0 delta is the transition function, mapping function. Q0 after accepting small a, it will be in Q1 state. So this is nothing but the transition, or I can represent like this: current state Q0 into current input alphabet small a, it will be in the Q1 state. So this is set of transition. But here in case of grammar, we are in the equation. So it will be like this: Q0 and after accepting a, it will be in the a small a, and let us Q0 represented by this variable, let us say capital A. So a small a, after accepting small a, it will be in the transition state like this. Now here there are some examples are there which will show the comparison between grammar and parent automata. So here x is the initial state, and after accepting small a, it will be in the y state, where y is the final state as it is shown by the double circle. So how to represent its equivalent grammar? So here you can see x is the variable. After receiving small a, it will be in the transition state. So terminal x and small a is the terminal. There is another one example. X state after accepting b, it will be in the y state, where y is the final state because it is shown by the double circle, and after accepting a, it will stay in same state. So now its equivalent grammar is this one. So this part is repeated, it's a looping statement. So x after receiving a, it will be in the x only. So this part is repeated. But when it will be it will be in the termination state, whenever it having b as input, it will be the terminated. So b is there, that time it will be terminated with x. After receiving b, it will be terminated. Same way, third example, x is the initial as well as final state, because x is shown by the double circle, and after accepting a, it will stay in same state after accepting n number of days. Okay, n is 0 to anything. So or n is greater than equal to 0. So for x, this loop is repeated. So x, if a 1 a is there, x 2 3 4 ax. But when it will be terminated, even if 0 number of a is here, so that's why x tends to epsilon. Context free grammar, which is defined by using 4 tuple. So CFG, G, which is defined by using 4 tuple. We know that up till now we have discussed the find automata, which is defined by using 5 tuple. DFA, which is deterministic find automata, which is defined by using 5 tuple. NFA, again which is defined by using 5 tuple. And NFA with epsilon, which is also defined by using 5 tuple. Two more definitions we have discussed. One is Mealy machine, another one is Moore machine. So that two machines are defined by using 6 tuple. Here CFG, context free grammar, G, which is defined by using 4 tuples, where G is equal to V, T, P, S. V, comma, T, comma, P, comma, S, where V is nothing but set of variable which are denoted by using capital letter A to Z. So variables are denoted in the production by using the capital letter A, B, C up to Z. T is the set of terminals and which are denoted by using small letter A to Z or digit 0 to 9. P is the set of production or equation. Means for example, if I will consider one example, A tends to small a tends to epsilon. So these are the production or equation, set of production, and this is nothing but the capital P. And S is nothing but the special symbol, which is also called as start symbol, where S belongs to the V. Here if we say that this grammar is this one like this, then here A is the start symbol of the grammar. CFL, context free language. CFL is the language which is generated by using CFG, or in short, the grammar which is generated by using CFG, context free grammar, is called as context free language. Or context free language grammar is generated by using the context free grammar. Every grammar generated word of language is generated by using set of production or equation a finite number of times. So grammar is generated by using the generate a word of language which is generated by using set of production or equation. Derivation of string should start from start symbol and final string consists of terminal. So whenever we want to generate any string, suppose with the help of this grammar I want to generate the string 0 1 0. Okay, if I am to generate this string, then derivation of string always start with start symbol. So what is the start symbol of this grammar? Yes is the start symbol. So I need to consider yes, and yes I am in production A1B. Yes I am in production A1B. Now I want to generate the string 010. So I need to replace this A with what? 0A. Okay, so I am going to replace that A with 0A. So now that production will become, I have replaced that A with 0A, and remaining production will remain same. Remaining equation will remain same. Again now I want to generate after 0, I want to generate 1, but A having no any production which will show the 1 as a termination. So I need to replace that A with epsilon. So I am going to replace that A with epsilon. So now string will become, this production will become 0 1B. Now 0 1 is over. Now I want to generate 0. So I want to generate 0 means B should be replaced with 0B. So whenever I will replace B with 0B, then 0 1 0 is formed, but B is remained. So I need to replace that B with epsilon because 0 1 string is over. So like this. So that's why derivation of string should start with start symbol, and final string consists of only terminals. So this B is replaced with epsilon, and now in a final string only 0 1 0 is there, and that is nothing but the terminals. Where in this grammar CFG G VTPS. So we know that grammar is defined by the 4 tuple VTPS. So V is nothing but the variables, and here there are 3 variables are there. Yes, A, B, because variables are shown by the capital letter. T terminals are shown by using small letter A to Z or digit 0 to 9. So here digits are there 0 and 1. P is nothing but set of production. Let us rename these production as P1, P2, and third production is P3. Okay, P3. So P is nothing but P1, P2, P3, and here for this grammar yes is the starting symbol of the grammar. So this is nothing but the context free grammar and context free language. Thank you.